Hey everyone, and welcome to this explainer. Today, we're pulling back the curtain on the hidden physics happening right beneath our feet. I mean, when you look at the ground, it just seems like solid dirt, right? But the reality is that the earth we walk on, the earth we build our homes on, is incredibly dynamic. We're diving deep into the fascinating world of soil moisture today, specifically focusing on two massive concepts: permeability and capillarity. So let me ask you something. How exactly does water flow through solid ground? We know it happens every single time it rains. But even more mysteriously, how can water actually climb upward, literally actively defying gravity? I know, it sounds like magic, but it's actually pure, beautiful geotechnical engineering. Okay, let's dive into this and set up the foundation for how we're going to understand this whole invisible world. All right, let's get into it. The tale of two forces, permeability versus capillarity. Starting with permeability, going with the flow. Think of the soil beneath us, not as a solid block of rock, but more like an incredibly complex, microscopic plumbing system. Permeability is simply the property of a porous medium that allows fluids to flow right through it. Now, what's really interesting here is the emphasis on the word porous. Pretty much all soils, to a greater or smaller degree, are permeable. The water isn't actually moving through the soil grains themselves, it's navigating through the tiny void spaces, those little empty pockets right between the grains. And perspective really changes everything here. From a big picture, macroscopic engineering standpoint, we basically treat the path of water flowing from point A to point B as a straight line with a uniform effective velocity. Simple, right? But the microscopic reality is entirely different. Down at the grain level, the flow is this tortuous, highly erratic path. Water is constantly dodging around this random arrangement of soil particles, speeding up and slowing down as the size of those tiny pores constantly changes. If we zoom out from that microscopic maze, this permeability creates massive underground water systems that we call aquifers. We broadly classify these into two types. First, you've got an unconfined aquifer, which is essentially just a free-flowing zone where the upper surface is the regular groundwater table. But then we have confined or artesian aquifers. This is where water is physically entrapped under pressure between incredibly dense, impermeable layers of earth. Engineers measure the potential of these massive underground reservoirs using the coefficient of transmissibility, which is basically a calculation of the rate of water flowing through a full vertical strip of the aquifer. Which brings us to what controls the flow? Factors of permeability. According to the famous Taylor's equation for laminar flow, there are a few primary characteristics that influence permeability, but the absolute biggest factors are grain size and void ratio. And the logic is beautifully simple. Smaller soil grains pack together to create smaller voids. Smaller voids mean it is incredibly difficult for water to squeeze through, which dramatically lowers the soil's permeability. A few other factors matter too, of course, like the chemical composition, the structural fabric of how the particles are arranged, like a flocculated, messy structure lets a lot more water through than a tightly dispersed one, and finally, the degree of saturation. To put that into a real-world perspective and show you how extreme this can get, let's look at a specific clay called sodium montmorillonite. Its permeability is remarkably low, less than 10 to the negative 7 centimeters per second. That is practically nothing. Even when it's incredibly porous, it effectively acts as a solid wall to water. It is the ultimate barrier. In fact, geotechnical engineers will intentionally take this specific clay and mix it into other soils when they need to forcefully block water from flowing through a construction site or a dam. And this is where we hit a really cool contrast. Permeability is all about water being driven downward by gravity or pressure, happily flowing through those void pathways. But what happens when the void sizes get so unimaginably small that a totally new physical property takes over? Enter capillarity, a force driven by surface tension that actively fights against gravity. Capillarity, water defying gravity. Think about how wild this concept actually is. Capillary rise is when water climbs above the groundwater table, completely against the pull of gravity. It creates what engineers call a capillary fringe, which is this zone of saturation hovering right above the actual water table. Oh, and here's a fun fact. The word capillarity comes from the Greek word capillus, which means hair. It perfectly highlights that the void openings you need for this phenomenon to happen are literally the width of a single human hair, or even smaller. Picture inserting tiny glass capillary tubes into a pool of water. Because of the intense attraction between the water molecules and the walls of the tube, combined with the surface tension at the air-water interface, tiny curved surfaces form at the top. We call these menisci. These menisci act just like tiny suction cups, pulling the entire water column upward into negative hydrostatic pressure. So the water isn't being pushed from below at all. It is literally being pulled and held in tension from above. So, where does the math meet reality down there in the dirt? Remember how we just said smaller voids mean lower permeability? Well, for capillarity, smaller voids mean higher capillary rise. In fine gravel, water might climb a mere 20 to 100 millimeters. Pretty small. But in highly fine-grained clay, water can climb anywhere from 10,000 to an astonishing 30,000 millimeters. That is 30 meters upward into the soil, completely defying gravity. Absolute madness. Moving on to the squeeze, capillary pressure. Now, this gravity-defying stunt definitely doesn't come for free. Holding millions of microscopic water columns in the air creates a massive physical reaction inside the soil itself. To figure out how intense this pressure gets, engineers actually measure it using a horizontal capillarity test setup. By forcing water horizontally through a soil sample inside a glass tube, they can isolate the forces at play. They measure the exact pressure difference right at the line of saturation, and that lets them calculate the negative capillary tension holding the water menisci intact. And when they run those calculations, the numbers are just massive. In silty soil, capillary pressure ranges from 10 to 100 kilonewtons per square meter. But in clay, that tension can reach anywhere from 100 to 300 kilonewtons per square meter. That is an unbelievable amount of physical force being generated just by microscopic droplets of water clinging to dirt. So why do we even care about this negative pressure? Well, that negative tension doesn't just hold the water up in the air, it physically pulls on the soil grains themselves. The sheer weight of that entire suspended water column transfers a massive compressive stress directly onto the soil's mineral skeleton. It is literally squeezing the soil together. And this is exactly why fine-grained soils, like those clays we've been talking about, drastically shrink and crack when they dry out or when their moisture levels change. You know, this whole incredible balance is also highly sensitive to the environment. For instance, a drop in temperature actually increases surface tension, which makes the water climb even higher in the cold. Conversely, if a flood fully submerges the area, capillarity stops entirely, just ceases, because that crucial air-water interface is totally gone. And on hot days, evaporation at the surface constantly pulls that highly mobile capillary water up and out of the ground, continuing a relentless cycle. Which leads us into why soil moisture matters, the ground beneath us. We've gone through a lot of microscopic physics today, but let's bring both of our forces, the flowing permeability and the climbing capillarity, together to see their impact on the macroscopic human world. The main takeaway here is that these aren't just abstract textbook concepts. Mastering these mechanics is the literal foundation of modern civilization. Without a deep understanding of fluid dynamics in soil, engineers cannot determine effective stress, they can't predict how much the ground is going to shrink and swell, and most importantly, they absolutely cannot design safe, stable foundations for our homes, our highways, and our skyscrapers. And that leaves us with one final thought. Right now, literally beneath your feet, water is endlessly flowing, climbing, and squeezing the earth. How might the invisible, relentless forces of permeability and capillarity be shifting the very ground your home is built on at this exact moment? It's a completely fascinating hidden world down there. Thank you so much for joining me on this explainer, and keep exploring the amazing science that holds up our world.